Welcome back. Now, in our previous lecture, we covered the energy and momentum flux of electromagnetic waves. As we discovered, momentum flux is better known as radiation pressure, and using it, we were able to calculate how fast a solar sail spaceship could go. So, I hope you've all come to the conclusion that electromagnetism has a lot to do with the electromagnetic spectrum. So, the electromagnetic spectrum shown here is the spectrum of wavelengths and frequencies that is characteristic of various mechanisms for producing and responding to electromagnetic radiation. So in layman's terms, it's every kind of electromagnetic wave possible. So the lowest energy waves are down here. Now the energy corresponds to a frequency and a wavelength. Now you've probably seen frequencies on your radio, if you still happen to own a radio of course. Now the channel is actually the frequency of the EM waves used to carry that particular station's signal. Now frequency is a measure of how often an electromagnetic wave goes up and down. So if we were to come down here and draw our usual electromagnetic wave, here. So the frequency is how many times it goes up and down in a certain unit length. Conversely, the wavelength is the distance between adjacent peaks of an electromagnetic wave. It's very simple to convert between wavelength and frequency just by using these very simple equations. So you can see here that both equations are related to the speed at which electromagnetic waves move. So using these two equations, have a go after this video to calculate the wavelength of a few radio station signals. So as we move away from the radio section and along the spectrum this way, we cross microwaves, infrared, the visible spectrum, this little bit here, ultraviolet, X-rays, and gamma rays. Now each of these names I have just said are used as labels that describe each of these different kinds of electromagnetic waves by their frequency, wavelength, and their energy. Now the EM waves that we are most used to dealing with are in the visible spectrum, this tiny bit here. Now stretched out we get this. Now the reason we're most used to this one is because this is the part of the spectrum that we can see with our eyes. Now, most of us can actually see in color, and now this is because of molecules in our retinas. Currently we understand that there are three kinds of molecules. Now, each molecule responds differently to different wavelengths in the visible spectrum. So each kind of molecule will respond less or not at all to a wavelength that is favored by the other two molecules. Let's call them R, G, and B. So our brains interpret signals from R molecules as red light, G as green, and B as blue. Now our brain can interpret a mixture of wavelengths. For example, a mixture of 700 nanometers, which is red, and 400 nanometers in blue, is interpreted as magenta by our brains. If all three of these molecules are stimulated equally, we see white. Now neither magenta or white is a color we see in the rainbow. Why do you guys think this is? Now, just to show how clever our eyes really are, there is an overlap in sensitivity between receptors. For example, yellow light stimulates R and G receptors. However, our color TV use closely spaced red and green dots to fool our brains into seeing a yellow dot. For those of us lucky enough to have biologically working eyes that can see in color, we can see the world in many shades. However, for people who cannot see, there is new research that may be able to help them in the future. So a group of researchers here at ANU actually looked into creating bionic eyes. Now these eyes send signals to the brain using the optic nerve in order to try and mimic what biological eyes do. But so far, they are not able to precisely integrate it into how color is seen by our eyes. And so the people who use the bionic eyes have said that they see shapes or shaded areas. The research is still ongoing, and so hopefully in the future they may actually be able to create proper bionic eyes that can see in color, just like we can.